So we're going to be looking at a practice free response question. So let me see if I can zoom in here. There we go. Too much. There we go. This is a elevator with a counterweight and a pulley. This is that type of problem. And when I look at this, my mind immediately goes to dynamics. So it does fit into the dynamics kind of unit, if you want to think about it like that. So we're thinking second law, free body diagrams, all those, right? Not too difficult. So let's see. Two guide rails for the elevator shown above each exert a constant friction force of 100 newtons on the elevator car when the elevator car is moving upwards with an acceleration of 2 meters per second squared. The pulley has negligible friction and mass. Assume G is equal to 10 meters per second squared. Alright, so usually with any type of second law problems, we like to identify forces on an object, right? That's usually what the first question will be about. So here we have it. On the diagram below, draw and label all the forces acting on the elevator car. Identify the source of each force. So they gave us a little elevator car right here. I'm going to actually move it up here. I'm going to draw it myself because I need a little bit more space than what they gave to do it. Okay, so we have to draw and label and then also identify the source. So this part is probably the one that a lot of people don't know where everything is. So let's start with gravity. Where does gravity begin? It begins at the center of mass. It always happens, it's exerted on the center of mass, the object's mass. So I'm going to give it the gravitational force, right? mg, or the weight. Now we want to look at the next obvious one, which is tension. Tension happens where it's connected to, right? Where it's being pulled. It's being pulled right here, so I'm going to put tension up here. I'm going to use capital T. And then we have the friction ones, right? If the elevator is moving up, friction likes to be opposing to motion, so we want to be pointing down. So that's going to be pointing here, where there's contact, right? It has to be where there's contact. There's two friction forces here. And let me draw the arrows on top of them. And this is part A. Not too difficult, right? Just the hard part is knowing where exactly does the source of the force happen. We drew in label, so we get all points for this one. This is A. Now we look at B. So now we start B, right? Calculate the tension in the cable for lifting the 400 kilogram elevator during an upwards acceleration of 2 meters per second squared. This one you just have to draw the Newton's second law equation in the vertical component, right? The sum of the forces is equal to ma. So what is the sum of the forces, right? I will first have to define upwards to be positive in this case, right? In fact, I'm going to draw it here. I'm going to define this direction as positive, right? Anything happening here, so this is a positive here, but as soon as we go around the pulley, anything going this way is positive, right? This is how I'm going to define it as. Okay, so let's begin. We have calculate the tension. So let's sum all the forces of the elevator. So we have the T, which is positive. We have the F's, which are minus, and then the weight of the thing, which is minus, right? Is equal to ma. I'm just going to go ahead and solve for T here. So it's going to be 2F plus mg plus ma, which is equal to, we plug in all the values we know, right? 2, the friction force, each of them is 100, so that's why it's 2 times 100. The weight is 400 times 10, because we're using 10 as g, and then the acceleration, so it's 400 times the acceleration, which is 2. And then we just sum this up, we get 200 plus 800, or no, not 200 plus 800, we get 200 plus 4,000 plus 800, there's 800, which is equal to 5,000. So the tension is 5,000 newtons. This is part B, not too difficult either. Part C, calculate the capital M, the counterweight, that it must have to raise the elevator car with the acceleration of 2 meters per second squared. This one's also not that bad. We want to look at the free body diagram of the counterweight. We have a tension pointing up and this pointing down, the weight, capital M, G, and T. So then we want to use Newton's second law to express this. We're going to use capital M, right, instead of lowercase m, because that's what the object in question is, right? You want to use the object in question as equal to MA, right? M represents the counterweight. I'll use it to do MA, capital MA. The sum of the forces are T minus capital MG, right? Kind of weird, right? But actually it's not T minus MG. It is the kind of the opposite, because the reason why it's the opposite is because of what I defined here. I defined it to be this direction, so it's actually MG being positive and T being negative. Just because of the way I defined it, right? You can define it your own way. Some people like to define it all at once, a direction. Some people like to define it twice, like one here and one here. But I defined it all at once, so we're going to stick with that. We have to stick with that convention throughout. So then let's solve for MG, right? MG. So I'm going to bring MA here is equal to T. I'm going to factor out an M, G plus, or G minus A, sorry. G minus A is equal to T. I'm going to say capital M is equal to T, G minus A. And now we need to keep in track of what's happening here. So I'm going to scroll down a little bit. Here we go. So T is the same exact thing as this, right? The tension's here, so let me go back to the drawing. This tension is the same as this tension, right here and right here. This and this are the same tension, and that's just a fact we need to know about pulleys, is that the tension will be the same. So it's actually 5,000, so we can plug in 5,000 here. What is the gravity? It's 10, right? Is it positive or negative 10? Well, by the convention, downwards on the right side is positive, so it should be positive 10. And then you subtract the acceleration, which is 2, right? 2, and since the counterweight is going downward, it should also be a positive value. So it's 5,000 minus 8, and then using a calculator, we get 5,000 divided by 8, it is 625 kilograms. That's the weight of the counter mass. So in all, let me just zoom out. We were looking at an elevator and a counterweight with some friction involved. Part A asked us to find and label the source of the force, which is done here. And then part B asked us to find the tension on the elevator car, which was easy because they gave us all the information here in part B and the stimulus. And we found it to be 5,000. And then we also had to first define that this direction, this, I guess, clockwise-ish direction is positive, and we should stick with that convention throughout the whole problem. So I stuck with it here. Instead of doing T minus MG, that's not convention. I already defined what the convention is. I should do downwards is positive, so it's this minus that instead of the other way around. I solved for capital M. I plugged in 5,000, and remember G, since it's down and on the right side it's positive 10, not negative 10. And then there we go. And I got the answer. So this is how you use Newton's second law and free body diagrams in practice. So this is it for this problem. So that's it.